Welcome back to our office hour. Today we'll continue with our chaotic presentation. We'll continue with our presentation of chaotic material, and we'll talk about the chaotic pendulum. So this is continuous nonlinear dynamics. So we've already discussed the logistic map, or bugs, and we saw that chaos can come in various forms, but even when there's chaos, there's some interesting structure down below. And that's a typical characteristic of nonlinear behavior. What we'll see today, and tomorrow, and probably the time after that, is how continuous systems like pendula also has chaos, and how those systems can be very similar in some of the structure to the bugs. Okay, so there's some universal behavior here. Okay, so this is the problem you have to solve. Actually, you have one of two problems to solve. The simple problem, the one which we spend most of our time developing in the chapter and which we'll discuss at length, is just the simple pendulum, single pendulum here, with an external driving force on the top. So that's a torque that moves it back and forth, length L, a mass m at the end, and has this, what looks like hair at the end of this red ball. That's just friction, some kind of friction proportional to velocity, so it's a wet friction. And the pendulum can move back and forth. Theta can be small, can be large. In fact, we want no small angle approximation, so we want theta to be large. And theta, which grows this way, you see, theta can be greater than 2 pi, or greater than pi. Theta equal to plus pi means it goes over the top. So over the top motion is allowed. 2 pi means it goes around completely in the counterclockwise direction. And minus 2 pi would be the clockwise direction. So we can have oscillations 2, 4, 6 pi, or negative 2, 4, 6 pi, depending on how many times it goes around the top. So that's the driven single pendulum. It's driven with a force. It has friction. Solve that problem. The other problem we talk about, and we'll leave this as extra, because many students now have seen the simple pendulum here, the chaotic pendulum, in their classical dynamics course. And if you've seen it there and studied it, understand it pretty well, try something new. So here's a double pendulum. So it's two masses, different values, connected by rigid rods, one of length L1, the other of length L2, and it just oscillates freely. So here there's no driving, but one mass in a sense drives the other, and that provides the extra degree of freedom that you need to have chaotic motion. Plus it's also a nonlinear system. So theta 1 and theta 2 can also go over the top, no restriction as to small angles. So if you've studied the single pendulum, study the double pendulum. You don't have to put in friction, you don't have to put in a driving force, but it's a very interesting system. And we'll tell you how to do that. We'll even give you the equations. Fine. How interesting are these systems? They're very, very interesting. So here, for the single pendulum, we have this movie we'll show you. And as you can see here at the beginning, this movie has two pendula. Okay? So these are two identical single pendulum. I know, two pendulum can't be single, but there's two separate single pendulums independent of each other. And they're starting here with initial conditions that differ by only 1 part in 1,000. And logically you'd say, hey, the physics, this is the real world. If they differ by 1 part in 1,000, I'm not going to see that with my eye. And that's correct. But it's a chaotic system. It's a nonlinear system. And so that the, I just jumped it around. So that it's very sensitive to initial conditions. So what's interesting here is you'll see how this very slight difference in initial conditions leads to different behavior. So stop talking and show the movie already. So there's the movie. They start off looking identical. They move around. Then at one point, they sort of balance on the top. One moves away from the top. Do it already. And the other doesn't. And there it is. Okay, the other sticks. And now they look like different pendula. So for most of the time, they're identical. But then afterwards, after that, they have different behavior. We'll study this some more, too. But it's a good example of what's interesting about these systems. So stop now. Good. Let's go on and see how we actually solve this problem. Here is our system. Okay? So we want to talk about a pendulum. We want to talk about several different characteristics. So here is our pendulum. Okay? So a pendulum, can swing. It has friction, which means it dies down, and has large angles, which means it can go around. And here it has large enough angles so it can actually go all the way to the top and then fall down and go over again. Okay? So that's also periodic motion. It's rotational motion, and this pendulum can do both. Okay? So what's happening here? Well, we describe the system in terms of physics by Newton's law of rotation. So rather than having the sum of the forces equal to mass times acceleration, we have the sum of the torques equals to the moment of inertia times the angular acceleration, d squared theta, by dt squared. Okay? What are the forces present? Well, the first force, the force that restores the pendulum back to its equilibrium position, is gravity. So there's torr minus mgl. So that is, that adds in just like that. So that's just restoring torque. The negative sign means as theta gets positive, torque is negative, pushing it back in the other direction. So this restores us back. So that's I d squared theta by dt squared is equal to minus mgl sine theta. That's the first term. Fine. The next term is friction. So that is just the little hairy ball here. And we see that the friction has some constant beta times d theta dt. So that's a velocity. It's the angular velocity. So the friction is dependent on velocity. So it's not a constant. It's a more realistic friction, which depends on velocity. And then we have the driving force. So we have this force at the top, or a torque, that tends to move sinusoidally back and forth if there's nothing else happening. So there's a sine, it could be cosine. Here it's cosine omega t times some constant. Okay? So that is our equation of motion, equation 1. It's usually written in a form more standard and a little easier to understand as equation 2. All we've done is divide through by the moment of inertia I. So what we have in equation 2 is d squared theta by dt squared is equal to minus omega 0 squared. What's that? It's a constant. Omega 0 is mg L over I, although it looks like mg L over L, but it's actually an I on the bottom there. So these are all I's. Okay? Neat. Okay? And that's just the natural frequency of the pendulum for small angular motion. Okay? So it's not necessarily the frequency which this realistic pendulum oscillates at, but it will be the frequency if it was very small oscillations and nothing else happening. So that's the natural frequency. Alpha is just obviously beta over I. It's just a frictional constant. And F, think of F as a force. It's the external force, or here it's the external torque divided by the moment of inertia. Okay? So that is our system. That's the system we have to solve. So how do we do that? Look at the next slide. Number 8. Well, we solve this by throwing it on the computer. Easy said, easy done. Okay? Well, what that means for us, we've had those lectures already. It means that we use RK4. That's what we recommend. You can try something else. You want high precision. So that's the fourth order Runge-Kutta solution for ordinary differential equations. And as you recall, what we have to do is somehow write our differential equation in the form of y dot, where y is a vector, several components, is equal to some force function, and that force function is only a function of y, the unknown, and time. Okay. So equation 1 is our equation. What kind of equation is it? We have to solve that. Well, it's a second order. Okay, second order because you have d squared by dt squared. It's time dependent, and it's time dependent because we have an external force which depends on time. It's not time dependent because theta is dependent on time, but there's explicit time dependence. Okay, that's second order, time dependent, and it's nonlinear because we have sine theta here. Okay, and as we showed down here, sine theta is approximately theta for small angles, but has higher order terms. So this is where the nonlinearity comes in. Okay, making this into the standard form, we just follow the usual trick. We assume the first component, the zero component of y, is just theta, fine. And then the first component, y1, is d theta dt. That being the case, then the two simultaneous first-order differential equations, there are 2 and 3 here that will be equivalent to equation 1, are just dy of 0 by dt is y1. That's just definition. The derivative of theta with respect to time is just what we call d theta dt, which is what we're calling y1. And then the real differential equation says that the second derivative of theta, which is just the first derivative of y1, that's what we have, okay, is minus omega 0 squared sine of theta. Theta is, of course, y0, so it's sine of y0, minus alpha d theta dt. D theta dt is just y1, right there, plus f cosine omega t, which just comes in. So equation 3 here is all we have to solve. And if you look at it, you'd say, is that it? Well, such is life, you know. It's not very complicated, you know, but it has everything we need to be more complicated than we can figure out. Okay, so that's good. You've studied pendulums before. You just maybe have not studied them when you can have all the angular motion, you can have all these forces occurring simultaneously, and it tends to make a difference. So let's look at the next slide. As simple as that equation may have seemed, it's already too complicated for us to start with. When you start, it's always good to have something simple so you can test your algorithm, which means you know an analytic solution to compare with. It's the best way of testing an algorithm. It also is good to test the physics, make sure we understand what's going on, that we're describing the system properly. So to start with, and I mean not just mentally, but that as well, run your program. You have all the software running already. Try out first the simplest system, which is just our pendulum with no friction, no driving force. So the equation of motion is just theta double dot is equal to minus omega 0 squared sine theta. And of course, what's interesting here is I want you to keep sine theta, okay? Because that's what makes this nonlinear, makes the behavior more interesting. It means there's no analytic solution to compare with, which is not very good for testing. So how do you test it? You test first by saying, let's just look for very small angles, small as possible, deviations from the rest position. Then we know the differential equation has sine theta replaced by theta, and we get our familiar friend, simple harmonic motion. Okay? So test your solution by seeing that you get simple harmonic motion for very small behavior. And then you know omega 0, 2 pi over t, is related to the period. So you can predict whatever value of omega 0 is, what the period should be. Okay? So that's what you should get. That's a good way of testing it. What if we have the real equation then? Well, the truth of the matter is there is no solution, analytic solution, for equation 1. As simple as it may seem, it doesn't have an analytic solution. I know if you look in the classical mechanics books, they'll say, oh, the analytic solution for the period is given by this funny equation. Well, yes, it's a solution for the period in terms of an elliptic integral. And what do you do with an elliptic integral? Well, you put it on the computer to compute it. So it's an analytic solution, but you don't have any real fundamental understanding of what it's like. But now that that's said, you certainly can compare your numeric solution, at least the period, to the analytic solution and see if that agrees. Or you can compare it with small oscillations to omega 0 and see if that agrees. So there are some possibilities, but that's how we want you to start. Okay? So that's your first problem. Always start off something simple. So how do you go about doing that? So on slide 18 here, we talk about how to implement your numerical solution. So take a look at that for a second. Okay, so we're starting off by trying to solve theta double dot is minus omega 0 squared sine theta. Fine. You have to always choose initial conditions. It really doesn't matter, but for this problem, it's very helpful to start with initial conditions so that the pendulum is at the middle and theta dot, its angular velocity, is non-zero. In other words, we're starting right here, always, but you give it some angular velocity so it can move in either direction. And then if you give it a big enough angular velocity, it can go over the top. If you just start off with large theta, the best you can do is try to have it balanced upright. But you want it so you can give it enough theta dot to eventually have it go over the top. Okay, so that's a good way. So start off with very small theta dots, minuscule, and then increase it till something interesting happens. So the first thing you want to make sure is we get simple harmonic motion down. Okay? So if theta dot is very small, and very, very small, we should just have simple harmonic motion so you can say, aha, I know the period t, or the period t should just be what? It should just be 2 pi over omega 0, whatever you put in for omega 0. Okay, so you know what the period should be. Make sure you get that. Not only do you get the period, you should get that right, the period should be independent of the amplitude. So as long as it's very small, change it a little bit, period shouldn't change. You should get that as your answer. Then we want you to devise an algorithm to compute the period. That's interesting. In other words, what we're saying is take your output from your program and deduce what the period is, not just by looking at it with your eyes, because they may not be that good, and we want some precision here. So how do you do that? Well, if you think about it, and think about the general case, we may have a very nonlinear system. So this might be the origin. We may have an amplitude that goes up like that, comes down like this, and then comes up like that. So if you just measure 1, 0, if you just say, okay, I start off at 0, I measure when it crosses 0, so that's obviously half a period. Well, it's not obviously half a period if it's not symmetric like this. So you want to make sure you have 1, 2, 3 crosses. You want the amplitude to cross 0 3 times, because then you know the third time, since it's a periodic system with a restoring force, it's always going to repeat, but it doesn't have to be symmetric. Then you know after the third time you have a full period. Okay, so that's the period. Good. So do that and determine the period for this realistic pendulum, for the pendulum with the sine theta. And then compare it. Compare it to what? I don't know. Compare it to simple harmonic motion. You should find, think about the physics. If you make the amplitude larger and larger, then the restoring force is not quite as great as theta. Sine theta is less than theta, which means the period should increase as the amplitude increases. Okay? So that's why you have to have your algorithm. Simple harmonic motion doesn't do that. That's a good comparison. Or you can try to compare it to the analytic formula from the mechanics book we gave you on the last page. That's also very good. So do that. That's very interesting. Test your algorithm to test that the physics is working. Okay? And as long as we keep the kinetic energy less than 2 mgl, we should get non-harmonic oscillations. So here's what we're saying. Imagine this being the full length. This is m at the bottom. So this would be a kinetic energy, move it up to the length. So that would be mgl. 2 mgl moves it up to the top. Okay? And this is saying as long as you keep it below the top, it should just be a simple motion, not simple harmonic motion, but it should be simple periodic motion back and forth. Okay? And that's what you want to do. Then, get more interesting. You're counting the period, and what we're saying is keep giving it, just nudge it a little bit more and more so that it keeps going up, and try to find the initial velocity that just gets it to the top. And when you find that velocity, as you get closer and closer, the period should increase. And in fact, if you can just give it enough velocity so it just stands on end at the top, you should get infinite period. And that's very interesting, because if you give it any more velocity, then it's going to go over, it's going to start rotating. And that critical condition, when it just gets to the top, is called the separatrix. Separatrix because it separates oscillation, which is periodic, from rotation, which is also periodic. And rotation go back and forth too. Okay, so try to do that. And then what we suggest for fun is you should listen to what periodic motion sounds like. Okay, so we have here harmonic motion periodic, and we also have non-harmonic motion periodic, and we have 2 ways to do this. So one of the things we've done in this class with the real live students, as opposed to you television people, is we've had the students take their oscillations and convert it into sound. Because, we spoke about harmonics and anharmonics and harmonic motion, and we can easily talk about sound. So let's show you how to do this. So on the CD that comes with the book, or on if you're using the digital version of the book, we have this built in. You can listen to applets or you can listen to motion. So here we have a sample of one of the web pages, which is about visualizing physics with sound. And we give a lot of details here, so you can actually try this out yourself. But here we show 1, 2, 3 figures, and these were just solutions of this same problem, this chaotic pendulum. This is what, if you just take the harmonic oscillator and convert it to sound, that's what it sounds like. It's kind of boring, but that's perfect harmonic motion. If we look at a realistic pendulum, we won't hear much difference. So let's move up. If you look at a non-harmonic oscillator, a little overtones, what you hear is something with more interesting. It has some overtones. Okay, and if we compare that to harmonic, which had no overtones, and now we can say, what if you actually have chaotic motion? Either you can do this chaos, or we did a ball bouncing around. It has frequency there, but that's the sound of chaos. Okay, and here on the web, we give you this applet, and it's called Hear Data, and this was written by one of the students. All these things are written by students. I never do any of this work. And so here, if you look at this applet, go down, he talks about it, then he says, let's run the applet. And you see what this applet is it just a box, and you throw your data in it, and then it turns it into sound. So here, for example, we can paste, this is a demo, and I'm not sure what that's going to look like. This is coupled anharmonic oscillator. This is good. It's a complicated system. Here's the demo. You throw data in. These are the data. And here we process it. Aha. And it shows you what the sound would look like for the data. And then you can play it. And you can look, this is it. And this is just playing the data. And what you should be hearing there is you're hearing several frequencies, but you hear a beating sound, which is what we've talked about. So this is available to you on the CD or in the book. You can listen to your own oscillations. It's part of the fun. So anyway, we've had too much fun. Let's get back to work. Okay. Look at the next slide, and really look at it for a while. It's a very interesting slide, and it's an important one. All the slides are important. I take that back. Phase space. So this next slide, number 26, talks about how to visualize motion in phase space. Now, phase space is an abstract space, which means that it doesn't really exist in the world in which we live, but we imagine it, and it makes life much simpler for us. Okay? If you try to look at even these motions here of the position versus time or velocity versus time, you have both two motions to try to look at simultaneously, and you also can have very complicated motions. And what phase space does is it says, let's take velocity as a function of time, plot that on the vertical axis, the ordinate, and plot it against the position as a function of time. So time enters parametrically. That's why this is sometimes called a parametric plot, but you never see time plotted. So that's a phase space plot. Phase space is a combination of velocity and position together. Some books, and sometimes it might not be velocity, it might be momentum and position, but usually that just differs by an M or an I, so don't worry about that. Okay? So here we have 3 phase space plots. They're easy to look at than to say. And the first one, let's start on the left here. The first one is what we have for simple harmonic motion. Okay? So imagine here having a simple harmonic well. So that's V of x, and that's on the top here showing you where we are. And then for each place, each volume place of V, we get an ellipse. Okay, for each value of E. And what does that mean? Well, it means that whenever you have simple harmonic motion, the orbit in space, or the phase space trajectory as it's called, is actually an ellipse. And as you can see here with the arrow, it's an ellipse in which the particle moves around this ellipse in an orbit in a clockwise motion. Why is it an ellipse? Well, if we look at simple harmonic motion, x of t is a sine omega t, v of t is omega a cosine omega t, and we have energy conserved, which it does if we have no friction, then the energy is kinetic plus potential, 1/2 mv squared plus omega squared m squared x squared. Ooh, well, that's just the equation of an ellipse in phase space. X squared plus v squared and some constants in front. That's an ellipse because x and v are the two parameters. And as the energy gets bigger, the ellipse gets bigger. That's all it's saying. So if we look back here, we can say, sure, if we think of a little ball being released in this punch bowl-like shape, at high energy, the ball rolls up to the same height and then back. Okay? And as it rolls back and forth, it goes around a circle. If we do it at a lower energy, here at the middle, let's say, the ball just rolls back and forth here, and then back and forth, then it goes through a smaller pendulum. Okay, so that's the phase space plot. Okay. What if we now have another trajectory? If we now have a potential in the middle here, which is not simple harmonic, has, in this case, quite anharmonic. Well, if we look at the anharmonic potential, we do the same thing. Let's say we start off with some energy. Let's go in the middle here. Here's our ball. And we know it's going to end up across, going to the same height it started. So it moves down, moves this way, and then it comes back. Okay, so it's starting here on this ellipse. It's moving around. Oh, I can't do this. It's moving around, coming back here. Ugh. Okay, it's going around the ellipse again in this closed clockwise direction, but the ellipse is still a closed figure. Okay, so it goes around. It still goes around the ellipse in this clockwise direction, but now it's not really an ellipse. It has a point here, okay, because it's a non-symmetric motion and it's non-simple harmonic, but it's still oscillatory. So the oscillatory means it goes around, but the ellipse just gets changed in shape. Okay, so that's, both of these are now attractive potentials, and they're both periodic motion. Harmonic is a nice ellipse. Even if it's not a perfect ellipse, then it wouldn't be simple harmonic, it'd be some other. And clearly, non-harmonic motion, aharmonic motion, would have some corners or edges, but still very much ellipse-like. If we now look on the right here, we look at a repulsive potential. What do we see? Well, if we start with a ball on top of this inverted punch bowl, well, it's just going to roll away out to infinity. Okay, and that just means we're starting up here someplace, we let go, the ball just rolls away. No big thing. If we start down, if we start down here someplace, start in the middle with a ball, it's also going to roll away. And so, that's here, it's also going to go out there. When we're in the middle, of course, if we actually have the ball in the middle, it has a choice. It's unstable equilibrium. It can move right, it can also move left out. And therefore, when we're here in the middle, you have several choices. It can move to the right, like that, or it can move to the left. So we get these very interesting hyperbolic points, which correspond to regions where there's some repulsion. And even though the lines look like they cross, they don't really cross. They just touch, because each one corresponds to a different trajectory, one to the right, one to the left. So, phase space plots. Now you know everything there is about phase space plots. Try to apply it to your problem. So let's look at slide 32. As we said, the separatrix separates off rotations from, these are rotations and vibrations. Okay? So if we look here at this plot in yellow, what we have is two things plotted on the same graph. On the top, we have theta dot versus theta on horizontal axis. So the top in red is a phase space plot, the standard form. And on the bottom, we have the actual potential for the pendulum. Okay, so there's just minus mgl, just cosine theta. Okay. So here's the pendulum, and we see that it's a periodic potential, of course, because if theta goes around an extra time, it just comes back. So here we're being careful. You could map everything into 0 to 2 pi, but we're not, because once you have over-the-top motion, theta can get greater than 2 pi, or it can get less than minus 2 pi. It can go either way. So this is the pendulum here rotating one direction, then rotating to the other direction. So what we see is that if we have small oscillations, we still have closed loops in phase-space plots, and that corresponds to our usual vibratory motion. If the pendulum gets very large, if we have rotations, we go over the top, and then we have what's called running solutions. Now, both of these are periodic, because they both correspond to repetitive motion, one that was bounded in some region where it vibrates, and the other keeps running. Separatrix is just this line here, okay? So it's just the one with the cross in the middle here that separates vibrations and rotations. And at the separatrix itself, is that a vibration or a rotation? You can't say. It's unstable equilibrium. You know, if this motion came around here and then just came back and came here and came back, that would clearly be a closed orbit. That would clearly correspond to a vibration. But if it came here and then moved on, and then moved on here again, that's clearly over the top motion, or moved here, over the top. So that could be either. So these lines, which look like they're touching here, don't really, because any one orbit would just go one way or another. These are just separate orbits. And why do I mention lines touching? Well, that's because in classical mechanics there is a theorem about uniqueness of solution of the dynamical equations. And that means that if you know the velocity and the position, you know what the motion is going to be, so it can't go both places. It can only go one place. So for any given set of theta and theta dot, it'll go one place. It may take infinite precision to tell you exactly where it goes, because at the unstable point, and that's always an issue. Okay, so this is the phase space plot. These points here are called hyperbolic points, where they cross. They correspond to unstable equilibrium, and we see that. That just corresponds to the pendulum moving at the top, and then it can move back, or it can keep going over. Okay, so what else can happen? Okay, so now you need to solve that problem. Solve the pendulum with sine theta, but no friction and no driving torque. Understand that. Make sure you understand the physics well. Make sure you understand the phase space plots well, and make sure that your algorithm is working well. I didn't talk much about the algorithm, but you know what the analytic solution is, and you should be able to reproduce the analytic solution to at least 7 or 8 decimal places, but actually you should be going to 11 or maybe 13. Okay, that's a lot. That means you might have to make very small time steps. But that's because now we're going to get more complicated motion, and you want to make sure whatever you see comes from the physics or the math and not from the algorithm, not from poor numerics. So better to make sure your numerics are very good and that you can get high precision. Say for a case without any friction, energy should be conserved to 13 places. Know what step size it takes to do that. And then as you start exploring these more interesting cases, it has nothing to do with the algorithm. It's really not noise. It's new physics, made in chaos. So let's start off here. Add friction in. So add a little of this hair to your red ball, some of that beta d theta dt with a minus sign, something that causes your system to lose energy. You could make it gain energy, but then it won't be as interesting. So if you just had a pendulum oscillating and then you add friction in, it should stop oscillating. Fine. But we want to have now also the external torque. And if you get the phases just right, whatever energy gets lost due to friction can be put back into the system by the external torque. So let's look at that. So here in this diagram, what you see is two different initial conditions, and they both start off with oscillations, and the oscillations die in both of them. Fine. Okay? Because they're big oscillations, and since friction goes like velocity, these correspond to big oscillations, and then concordantly large velocities, there's a lot of frictional force, lots of energy lost to friction. But then as the amplitude gets smaller, the energy lost to friction starts matching the energy being put in by the driving torque, and the oscillations become stable, constant amplitudes. In phase space, what you see is you're starting off here with some orbits, and they're spiraling in because they're losing energy. But then as they lose energy, they begin to get a balance, and you begin to get what's called a limit cycle, when the average in one cycle, the energy lost to friction is equal to the average energy gained by the external torque being put in. Okay? And you could say, okay, but that must be miraculous. And as I said before, no, it's not hard to obtain, because you start off losing more energy than is being put in, so the amplitude gets smaller, and it goes obviously then through the point where the energy put in just matches the energy lost by friction. Fine. You could also do this demonstration or test your method by having no friction and then just driving the system. And that would be a resonance, where you're putting energy in, and if you get the phase right, the system blows up, gets very large. Here, you get both effects coming in. They cancel each other. Okay, so we're nearly done to send you off to work. Now it's time for you to put all the pieces together. Okay. Look at the full solution to your problem, which means friction, driving force, and no longer restrict yourself to small oscillations, which you should have been doing even before, just to make sure you know what's going on. And you should see different kinds of behavior. What you really want to see is complex behavior, which is the small amplitudes get bigger, and you want to look not just at the phase space plot, but also at the individual amplitude as a function of time, and see that it looks pretty complicated. We'll show you some of these. And then see what happens when the system approaches chaos. What does it mean to be chaotic? And in particular, how chaos may be complicated, may have a lot of degrees of freedom, but it's not going to be as bad as a random behavior, it's not chance. So that's for you to look at. So how do you describe, how do you explore a system like this? Well, it's not easy because so much can go on. And we actually have a 4-parameter space. If you think about it, we have friction, we have the gravity, omega 0, we have external torque, and we have the external frequency. And so don't vary everything at once. Try to keep as much the same as possible. So you start off with fixed parameters. Those are the parameters I just mentioned. And then what you want to do with all of these external parameters fixed is to say, let me have all possible initial conditions, all x0s we call them, but they could be velocities, and then look for all time. And what you want to see is how your system flows, as it's called, through phase space. All the possible places through phase space. And what you should get are diagrams like this. And the system, its behavior, can look very complicated if you look at the actual angle. We'll show you an example of that shortly. But when you plot it up in phase space, you see these geometric figures. And that's the reason we do phase space. Okay? The reason why phase space is so much simpler than looking at the behavior as a function of time is we replace these complicated oscillations by geometric figures. And our mind likes geometric figures. And here, even though these are complicated geometric figures, they all look very much like those ellipses. And so this is obviously a system with periodic vibrations and some rotations where it goes over the top, but really just one set of rotations, because there's only two of these ellipse-like figures. And here, if you look at it, you could say, aha, probably it starts off initially here, and then it jumps to the other side, and that's where most of the motion stays. So you can figure that out. Okay. So what we're saying is chaos can be complicated, but it's not a mess. There's nice aspects underneath. The figures will be similar to the ellipsis, similar to what you saw for simple harmonic motion. They may get distorted, but regardless of how complicated and regardless of how many initial conditions there are, the system always likes to return to these figures. Okay? If the figures are closed loops, like we see here in red, that's obviously periodic motion. Okay? And if they go over the top, then that's running motion. Okay? Or where you have several ellipses connected. What you see, though, is even when, if you run the simulation for many, many cycles, and feel free to run as much as you could, you won't get a black page, you won't get fog, you'll just get these figures here, maybe looking a little darker. They're called attractors. Okay? And they're attractors because the system appears to be attracted to them. They like to come back to them, they return to them. That's where the basic structures are that describe the system. Okay? A random motion would fill all of space, just a cloud. Okay? And these bands, these dark bands you can see here, are very interesting. What do those dark bands represent? Well, these dark bands represent, here you see it, here it comes around, you see some here in red. They mean that the system is sort of flowing from one set of conditions to another set of conditions, one phase space diagram, one ellipse to a nearby one, continually. But if you think of the fact that each ellipse represents like one simple harmonic motion, we have a system, and this is the description of chaos, in which it's really a bunch of harmonic motions occurring, but rather than all occurring simultaneously, they're occurring sequentially. So the system's starting in one place, it moves over, it's going to another frequency, it may jump around here even to the other side, but then it comes back. So these bands are an indication of chaos. That's where the system is hypersensitive. In other words, you really can't say if it's here where, why it's going to stay here and not move over to someplace else. It obviously just flows back and forth. That's the hypersensitivity. The slightest change can move it around. And we have analytic tools. They're discussed in the text: Lyapunov coefficient, fractal dimension, Shannon noise analysis, to show what's going on, to show that you can understand some of the structure within chaos. So I think that's about enough for now. It's time for you to take a break, time for me to take a break. Go into the lab, run some of these simulations. First, run simple, and then move up and try to understand. So we'll come back and let's talk then about what you should see in your simulations and try to make sense of it. But for now, go ahead and get to work and try this out. Bye-bye.